Okay, so let's get started. So last time we finished the process we're critics of, and we started a few examples. We're going to finish those examples. Say at the moment, so let's jump into it. So I believe we did up to C. So let's just start from D. We're doing the partial fraction decomposition. Last time. Let's see what we remember. What would be the first step here? Yeah?
We put equals a over x plus 2 and then plus b parentheses plus b x squared plus 2 and then parentheses squared.
No? What's off here?
Oh, the x squared.
Yeah?
It's supposed to be x squared for both of them, and then we have to
Okay.
add ax plus another constant.
Right, so once that's x squared, the top needs to be 1 degree lower. So this should look like ax plus b, and this would look like cx plus d. That's the first step. All right, so now that we have that, then what? What was the next step?
Multiply by the denominator on the left side.
Of this side. So we're going to multiply through by x squared plus 2 all squared. We will obtain 8x cubed plus 13x equals ax plus b times x squared plus 2 and then plus cx plus d. Okay, now what do you want to try here?
Expanding it.
Hmm?
Expanding the right side.
Okay. So you probably glanced at this and realized there's really no convenient number to plug in for x. Probably expanding grouping like terms would be the more straightforward way to go here instead of plugging in random values. I'm guessing that's what you thought. Let's actually do it then. So we'd expand the right side. Ax cubed plus 2ax plus bx squared plus 2b plus cx plus d. Then what?
Group together the constants and they're the same.
Group together the like powers of x. So we have a cubed term, we have a squared term, we have actually two x terms. So that's 2a plus c times x. These are both of those. And we have the constant term 2b plus d. This is all equal to 8x cubed plus 13x. And what do we do from there? Yeah.
Like match it up. Like
Match up the like
coefficients.
coefficients.
The fx.
So the x cubes on the left and right must be the same number of x cubes because it's an equation. So that must be true. The number of x's on both sides must be the same. So this must connect to that. You should also notice that we don't really have an x squared or a constant term visible on the left side, but how we deal with that is we simply just pretend they have coefficient 0. So there's a 0x squared over here, which I would match up with the b, and then the constant term is also 0, which I would match up with that. And ultimately, collecting all of these guys, I get the following system of equations. A equals 8. I would also get that b equals 0. I would also get that 2a plus c equals 13. I would also get that 2b plus d equals 0. So what would happen here?
A equals 8.
So we know that a equals 8, we just got that for free. B equals 0, got that for free. And
Can you
because a equals 8, I can plug it into this one and solve for c. So if I plug in 8 here, that's 16. Move it over, I would get c equals 13 minus 16, which is minus 3. And since b is 0, I would plug that in here. I would also get that d is 0. So I would use this and find that. And so ultimately, the 8x cubed plus 13x all over x squared plus 2 all squared, I can rewrite that as 8x over x squared plus 2 minus 3x over x squared plus 2 all squared. So that's breaking up this bigger fraction into two smaller ones. We're not required to integrate here, but as you can imagine, if we had to integrate, dealing with these would be much nicer than dealing with those. How would you integrate this part? Substitution. U equals x squared plus 2 will do it. What about this part?
Substitution.
Also a substitution. U equals x squared plus 2. Yeah. Questions on this? So you just really want to run through a few of these just to make sure you have the process down and you can deal with all scenarios. Let's go through the next example, which was E. How do you deal with that one?
A squared minus b squared. So it's x minus 1 is plus 1 in the denominator.
Nope, there's something to worry about first.
So you can add and subtract one from the top, so you could break it up. Since the
Right, why would you think that as opposed to factoring the denominator?
Because the power is the same right now.
The
so-
powers are the same. Notice here, the degree of the top is 2, the degree of the bottom is 2. Whenever, this means we have a non-proper fraction. This means that because the power on top is greater than or equal to the power on the bottom, the partial fractions method actually won't work on this. If you do it, you'll end up getting the wrong coefficients. So what you will do is try to find a way outside of partial fractions. Now there are a couple options. You might just add and subtract 1 in the numerator. So how do you know what to add and subtract? So try to get denominator in numerator. So when the degrees are the same, try to get the denominator in the numerator, then subtract terms as needed so that the value of the fraction does not change. So that's actually one of, I would say, two main options that you have. There are many options in general. But the denominator here is x squared minus 1. I want to get that in the numerator somehow. So what I'm going to do is I'm going to subtract 1 from the x squared. That gets me the denominator. But then if I just subtract 1, that changes the value of the fraction. So I add 1 to balance it out so that this is actually equal to that. It's just more convenient because now I can actually split this guy into that. And as you may be aware, maybe, especially in situations where the highest power is larger than the power on the bottom, or you just can't see what to add or subtract to make this kind of thing happen, you do have option 2, which is to do long division. And so basically that would look like x squared. You're dividing that into x squared minus 1. We're dividing that into x squared. X squared to x squared goes 1 time. Take the 1, multiply everybody. Subtract this from the top. The x squareds die. You would end up with a plus 1 over here. And so x squared to that can't, so that's the remainder. And so the result, if you take this guy, the result is going to be 1, which is the quotient, plus the remainder over the divisor. It's just a standard division trick, and you'll end up in the same situation. So either way. But usually when the highest power is the same in the top and bottom, a trick like this would be quicker than long division. But if you don't see it, or the highest power is larger than the one in the denominator, just jump into long division. And you can get to the same point after a few seconds more. So now that we're here, the 1 plus 1 over x squared minus 1, now the partial fractions thing can work for the second piece, because the highest power on the top is 0, highest power on the bottom is 2, which means that can split into a partial fraction. When you would actually factor the denominator and split them up. Because we realize that this guy here is going to be an x minus 1 times an x plus 1. Now, this represents the case where I told you about that trick last time. This is just a product of linear factors that are not repeated. So you can do this kind of cover-up method. And so, figure out what makes the denominator here 0. 1 does that. Cover it up, plug in 1, you would get a half. What makes this 0? X equals minus 1. Cover that up, plug in minus 1, you'll get minus a half. And that's actually the partial fraction that's equal. Or, of course, 1 plus, let's say you forgot that. Don't sit there and freak out. You're just going to, well, you would ignore the 1 for a second. Just look at the x minus 1, x plus 1. You multiply both sides by the denominator on the left. And for this, plugging in convenient values will work. So if I plug in a minus 1, this is going to die. I would get 1 equals minus 2b. So I get that the b must be minus 1/2. And if I plug in plus 1, this guy's going to die. I would end up with 2a, and you'd get a equals a half, and which is exactly what we had before. Takes a little bit longer. It's nice to know multiple ways to do something, because sometimes you're in a quiz or a test or something, and you know certain things just actually leave you. But if you know 5 different ways to do something, it's hardly likely that you're going to forget all 5. And if you're in a situation where you'll forget all 5, then your problem isn't math, it's something else, and you need to work on that, which we can talk about later. Questions? So yeah, step 0 to partial fractions. Always check that the highest power on top is smaller than the one on the bottom. Because if it's not, you can't jump straight into the method. You have to actually reduce it first. Now let's actually do what we're all here for, integrate. So A was the integral of 4x squared minus 3x plus 2 over 4x squared minus 4x minus 3. Okay, go. What do you do here?
Divide.
Divide. Okay. Long division. Do we need it? See any other way?
You do minus x minus 5 plus x plus 5.
Yeah, we could actually. The highest bar and top and bottom are exactly the same, so I'll probably try that whole subtraction thing, adding and subtracting something convenient. So that's there. What I'm going to do is to get the denominator in the top, minus 4x minus 3. I just throw those guys in. Now I just want to make sure that I didn't actually change the value of anything. Originally, it was a minus 3x. So if I throw a minus 4x here, what do I need to balance it with?
Plus x.
Plus 1x, right? So the minus 4 plus the 1x is going to give me back the minus 3x. Originally, there was a positive 2. I threw in a negative 3. What do I balance it with?
5.
Plus 5. So this guy actually breaks down to the integral of 1 plus x plus 5 over 4x squared minus 4x minus 3. Now obviously 1, no problems integrating that. So we now start to focus on this guy. So now let's deal with the x plus 5 over the 4x squared minus 4x minus 3. How are you going to deal with that?
Factor the denominator.
Right, so the highest part on top is lower, so we're going to factor the denominator. What does it factor into?
Two x plus 1 times 2x minus 3.
And do a quick check here. The product of the first terms gives us the first term. Product of the last terms gives us the last term. To figure out if it works for the middle term, you multiply the two inner terms, you would get 2x positive. Multiply the two outer terms, you would get minus 6x. If I take a plus 2x minus a 6x, I do get a minus 4x, so yeah, that was good. It's a good factoring. So the next step is actually you're going to break this up. 2x plus 1 and 2x minus 3. Now it turns out that these are linear non-repeating factors. So you don't even have to go through the partial fractions method as shown, although you could. Details left to the reader. I'm actually just going to do the shortcut. So x equals minus a half is going to make this 0, right? So I'm going to cover that up and plug in minus a half. So I'm going to get minus a half plus 5 over minus 1 minus 3. So that's going to give me, well, 5, I can think of that as 10 over 2. So in the top here, there's 9 over 2, all over minus 4. So this gives me 9 over 8. And over here, x equals 3 halves makes this 0. So I'm going to cover this up and plug in 3 halves. Plug 0.0350, that's going to be 4. Again, the 5 is 10 over 2, so that combines to 13 over 2 over 4, or in other words, 13 over 8. That goes in the top. So now if I call this I can now start to clean things up a bit and come back and compute the sky. This implies your I is going to be equal to the integral of 1 plus 13 over 8 over 2x minus 3 minus 9 over 8 2x plus 1 dx. Integral of this, x. Integral of that,
1/2 times 13 over 8, 10 2x minus 3.
good.
Half of that.
So technically there was a substitution, u equals 2x minus 3, but that's the kind of substitution where after you practice a bunch of substitutions, you can pretty much do it in your head. So this is going to be 13 over 16 ln of 2x minus 3. And this one?
9 over 16 ln 2 is
2x plus 1. There's your integral. Questions, concerns, comments? If you tried them on your own, which hopefully you did, you should be comparing what I'm doing to what you're doing. If you got stuck, assess where you went wrong or what you neglected to do. If you did something where you're sure it's right, but your answer doesn't look like mine, then you'll probably have to do a little calculation to make sure that your answer is equivalent to my answer. And then just decide, did you prefer what you did or what I did? And you pick one way, and you always do it that way. Just go with the preference here. So that's the first one. I would integrate this horrible looking guy. Okay, what would you try here? Yeah.
Substitution.
Okay, what would you substitute?
U squared is x.
U squared equals x. By the way, you can realize that what that means, it's actually equivalent to saying u equals radical x. This would give us 2u du equals dx. And so what you actually end up with is radical x is actually u, and the x is actually u squared, and the dx is actually 2u du. So we end up with 2 times the integral of u squared over u squared minus 4 du. How do we do with that guy?
Tricks up.
Huh?
Tricks up. No.
Not wrong, but not preferred. If you were to do a trig sub, what would the trig sub actually be?
it's x squared minus a squared,
Yeah, so
so x equals 2 secant theta.
yeah, so you could do a trig sub here. And if it's the first or only thing you see, I would just jump and do it. So u equals 2 secant theta could work here. And I encourage you to even try it and see how you like it, but I'd rather not use a trig sub here. So if I take that out of the options, what would you do here? Yeah.
Minus 4 plus 4 in the numerator.
So this would become 2 times integral of 1 plus 4 over, well, u minus 2 times u plus 2. How do we deal with that? Well, it's going to split up over these. U equals 2 makes this 0, cover that up, plug in 2, I would get a 1. U equals minus 2 makes this 0, cover that up, plug in minus 2, I would get a minus 1. So those are the partial fractions. And from here, we can wrap up pretty nicely. And that equals 2 times radical x plus ln of radical x minus 2 minus ln of radical x plus 2. Let's see. Did anyone actually do this with trig sub? Like actually work through it? Well, you can do it. Tell me what you like more. Personally, I like this one more. You do the trig sub, you have to convert everything to trig functions, you have to integrate it using some trig integral technique. Then you're going to have to do SOHCAHTOA to change it back to x's. You'll eventually get here, but I think it's a lot less efficient than doing this. Questions on this one? I know I've been hating on trig sub a lot in this class, and it's probably not the right thing to do. You know, like sometimes, you know, parents, they hate math, they have a fear of math, and they download that on their kids. Like, your math is the worst thing in the world, and the kid goes, "Ooh, you know, you guys probably walk away thinking of demonizing trig sub all the time. It's not that it's bad. Don't take that away. It's just that for like Calc 2, there was very often a much more efficient, time-friendly way to get to the answer. And back when I was in Calc 2, I kind of followed the strategy that I gave you guys. So I was like, in Calc 2, I want an A, and A means a 94, which means every time I want to practice a homework, I pick 20 problems, and I can only get 1 wrong. And if I get more than 1 wrong, I pick another set of 20 problems, and I do it again. And I kept doing that. You can imagine doing that with trig substitution leaves a certain kind of dark energy with you. Like, by the time over a weekend I'm doing 60 trig substitution, I'm kind of like, this thing sucks. And that kind of stuck with me. And then you do something else, you're like, this was so easy, why didn't it? Yeah. But yeah, it's a valid option. If it's the thing you see or it's the only thing you see, don't waste time trying to think of a method that's going to look cool or something like that. No, just do what you know, don't waste any time. But if you're ever thinking trig sub, I would probably pause for a second and be like, do I really need the trig sub though? Is there another way? And if you find another way, then I would take that. Okay. Let's look at e to the x over. Okay, go, plan of attack. Yeah?
In substitution, du equals e to the x.
Okay, so your du would be the e to the x dx, and then this guy is going to become pretty much 1 over u squared plus 1 times u minus 1 du. Okay, and how do we deal with that? Yeah.
Would you separate the two? Partial.
Yeah, okay, so what do the partials look like?
U plus b over u squared plus u plus 1. And c over u minus 1.
Okay. Now, let's deal with this for a second. So we have 1 over u squared plus 1 times u minus 1 equals deal with that. Okay, so the trick we used before, remember it only works with non-repeating linear factors. So you could actually do it to get the c, but you're out of luck using it to get u. So you might actually do it to get the c, but since you're going to need something else to get the a and the b, let's just continue. So multiply through by the denominator on the left, I get 1. Here I would get au plus b times u minus 1. And here I would get c times u squared plus 1. I can solve for the c right away. Like if I set u equals 1, that'll kill this whole term, and I would get 1 equals 2c. This means c equals 1/2. Okay,
Shouldn't there be a u instead of 1?
come again? Where?
So it's 1 in the numerator, right? Is it 1 or u?
Oh,
see
I don't know where you're talking.
Yeah, I understood. That's fine.
Okay. And again, for comparison, what you will notice is if u equals 1 would make this 0. So if you cover that up and plug in 1, you actually do get a half. So you could actually get the c a lot quicker. But it was there, so I just used it. Now, for the other ones, I would probably do something like u equals 0 seems pretty convenient here. That's going to kill the a. So I would have minus b and plus c, but I actually already know what the c is, so that's not too bad. And so I would have 1 equals minus b plus 1/2. And so this means that minus b equals, I'll move this over, 1/2, and so your b equals negative 1/2. And so now the only guy to find is the a. Maybe plug in something else like a u equals 2. And if u equals 2, I would get 1 equals 2a plus b times 1 plus 5 times c. But I actually know what the b is, minus 1/2. And I know what the c is, 1/2. So this becomes 5 over 2. So this gives us 1 equals 2a plus 2. This means that moving that over, I get minus 1 equals 2a, or a equals minus 1/2. So this means my integral now becomes, they're all like halves. So let's actually factor out a half here. And so we'll have b minus u minus 1 over u squared plus 1 plus 1 over u minus 1. Now, psychologically speaking, that does feel slightly annoying to me, so what I would use, we can pull that out. So this will be a u plus 1, and then put the minus over here, and that seems mentally less exhausting for some reason. Okay, so these are the partial fractions. How do we continue? What do you see? Yeah.
Well, for the u plus 1 over u squared plus 1, you just do like another letter substitution for u squared
Okay.
plus 1. And then, for the 1 over u minus 1, it's just the ln of u minus 1.
Sure, but think through the first option. What would be the consequences of the substitution you just chose? See, I said t equals u squared plus 1. What's going to happen?
It won't cancel out with anything.
Huh?
It doesn't cancel out.
Right, our dt is going to be 2u du. So there's the u here, but there's also a plus 1. Now,
Oh,
not
right.
the end of the world.
Yeah.
You could actually just rewrite the u plus 1, but that's a little bit more clumsy. So the plus 1 just, it prevents a clean substitution being done.
Could you just rewrite it as u over u squared plus 1 over u?
Okay, that seems a little bit more manageable. What happens to the first part?
Could use substitution here.
Right. Should be one you can do in your head here, and you want to practice that as much as possible, doing things in your head. It'll help you get to methods faster as well as just, it's good training. So if I were to do t equals u squared plus 1, I get 2u du. I'm going to have to divide out the 2, so it should be a 1/2 ln of u squared plus 1 at the end of the day. Right? And that one, what's the integral of 1 over 1 plus u squared? Arctangent. And the 1 over u minus 1. Integral of that.
ln u minus 1.
And what was our u? E to the x, right? That was it. So it's 1/2 ln of e to the 2x plus 1 plus arc tan inverse of e to the x minus ln of e to the x minus 1 plus c. Absolute value is optional here, but I would keep them just to be safe. It's not wrong to keep them, and there are cases where it would be wrong to not use them. Questions? This is a nice thing in terms of it's not monstrously complicated, but it's definitely showing that you have to have a bunch of things, a bunch of techniques in your head all the time. You never just get into partial fractions and you only have to worry about partial fractions. No, you always have to see, oh, a substitution might pop up, me needing to remember an inverse trig function might pop up. Yeah, you gotta kind of be so familiar with these guys that you can kind of roll with the punches as they come. And don't really know of a much better way than just doing a bunch of integrals. There's another way that's really useful and a lot less time consuming than you doing a bunch of integrals, but I'll probably talk about that at some other point. Maybe in recitation. Let's get through the rest of these. D. Okay, ideas. Substitution, what do you substitute? Equals sine x. Your du is going to give you the cosine x dx. So this integral just becomes 1 over u times u minus 1. That looks like a straight up partial fractions thing. Non-repeating linear factors, so I'm going to do the cover-up method. U equals 0 makes it 0, cover that up, plug in 0, minus 1. U equals 1 makes it 0, cover that up, plug in 1, plus 1. And that's a couple easy ln integrals right here. So we would have minus ln sine x plus ln of sine x minus 1 plus c. And that's okay. Just to note, chances are if you're practicing this from your textbook will probably write it as one big ln as opposed to a sum of two ln's. So you just use the log rules here. And that is an alternative answer form. Yeah, so that wasn't so bad. Okay, how would you do this one?
Tricks up.
Tricks up. Pretty straightforward. What would be the trig sub?
X equals tangent beta.
Yes, perfectly fine way. It would be a very common way to attack this one because a regular U substitution you realize wouldn't really work out in a nice way. However, again, let's purposefully avoid trig sub here. If I didn't want to do trig sub, what's another option? Yeah.
Like subtract 1 and add 1 in the numerator.
Do a what?
Just add 1 and subtract 1 in the root itself.
I'm not sure what you mean. Add 1 and subtract 1 where?
Inside the root. Inside.
Okay, how does that help?
No, I don't think that would work. I don't think that would work.
What were you seeing?
No, that's incorrect.
Yes, other suggestions? Yeah.
Could you square the top and bottom?
No, you can't square the top and the bottom.
Multiply by the root.
Right? In general, you can't square something if there's no equation to balance it off. So like, let's say you had a half. Ryan decides to square the top and the bottom. Now it becomes a quarter. You've changed the value. Right? So you can't just get rid of the radical. There is a valid way to get rid of the radical though. What do you think?
Natural log.
Yeah?
You multiply with the conjugate.
What's the conjugate here?
1 minus x squared. Like square root of 1 minus x squared.
Okay, let's work through that. What happens? You'd end up with 1 minus
X to the
x to the 4th
fourth.
over, yeah, that ends up being not, it's even worse. So nope, and that's also not the conjugate of that. You need two separate things for the conjugate in that form to work. You have one radical. Other options.
What about natural log?
How would I get a natural log in there?
E and ln. And then get rid of the power.
So you want the e to the ln of this thing?
Yeah.
And then integrate that? I don't know. I mean, that's a good trick for limits, but I don't see applying that working out in integrals often. Go again, another stab at it.
Multiply top and bottom by the numerator. Get rid of the radical top.
Okay, so you'd end up with 1 plus x squared over x times radical of 1 plus x squared. Does that make your life easier? Okay, I'll give you a hint. A substitution. Think of substitution. What's a nice substitution here? Yeah.
Could you do u squared equals 1 plus x squared?
Oh, interesting. Let's follow this one. 2u du is equal to 2x dx, so your u du equals x dx. And how would I get that to work? Well, then put an x here, multiply and divide by an x, that doesn't change the value of the function. So now this guy becomes the integral of, u is going to be the radical of this, so that's just a u. The x dx becomes u du. In the denominator, I would have x squared. From here, I can solve for x squared. We get this integral. Yeah.
What happens to the x? Like when you plug in x dx.
Yes.
Wait, actually, I missed something.
I multiplied and divided by x.
Oh, okay.
So this part here is the u du.
Okay, that makes it.
And this part here is the u. And then solving for the x squared from here gives me the u squared minus 1. We'll deal with this in the typical way. It's going to be 1 plus 1 over u squared minus 1. Right? By going to do minus 1 plus 1. Split it up, I get 1 plus the other thing, which this thing just breaks up into u minus 1 times u plus 1. U equals 1 makes this 0, cover that up, plug in 1. U equals minus 1 makes this 0, cover that up, plug in minus 1. So, integral u plus 1/2 ln of u minus 1 minus 1/2 ln of u minus 1. Let's see. And my u is actually the square root of 1 plus x squared plus 1/2 ln square root of 1 plus x squared minus 1 divided by the square root of 1 plus x squared
Should be
uh,
plus, right?
plus 1. What's that? Now, based on the answer, think of what doing a trig sub would have involved you doing here. And maybe even try it out. Try actually the trig sub version. I think we actually did that by trig sub. So that's why I deliberately wanted to avoid it here. Yeah, so there's another option. So you also definitely want to practice building up your intuition here. So knowing when a suggestion would work out in your favor versus not. At the end of the day, you know, I hate to sound like Sun Tzu or something, but the battle is won in the mind. Right? The integral should be dead before you put your pencil on that paper. You should see its demise laid out before you. And it's more than possible to get to that point. It just requires a certain amount of practice and a certain amount of strategy, which I will talk about pretty soon. You should be able to look at an integral and kind of know, oh, I can do this and do that. So it's very important that you actually practice that. That's why I'm asking for you guys to guess. It's not to embarrass you or something like that. I want you to actually see what your guess is, what the consequence of a certain kind of guess is, and what the consequence of another kind of guess is. Because then that's how you start to learn, oh, these kinds of guesses tend to work when I see these kinds of patterns. You kind of want to be there, and you'll start to see how it's unfolding. Thinking if I want to go through these, the last two, or spend time talking a little bit more about strategy. Let's try to go a little quickly. What happens here?
It's partial fractions.
Okay, how do I get it to work?
The denominator is x plus 4, x minus 1. Oh, it's cubed.
It's a cube. Yeah, yeah, it's very sneaky, huh? Look out for that. Yeah.
Can you do u sub on for the whole denominator? Because the derivative.
I don't know. What do you get?
U is equal to x cubed plus 3x minus 4, then du is equal to 3x squared plus 3. You factor out the 3, and it's 3 times the top.
Yeah, no partial fractions. That one kind of faked you out there. This actually would give you the integral of 1/3 1 over u du. So ln of u plus c, which is 1/3 ln of yeah. this one. Expect the unexpected. It's like you're in the partial fraction section. Jhevon wouldn't ask you something where you don't actually need partial fraction. You never know what I'm going to do. You don't know. Okay. I'm a math teacher. Obviously, there's something off, right? Yeah, that one's a little harder. Try it for next time. I want to talk about, like a general strategy here that should inform how you kind of approach an integral. So, I gave out the quizzes and a few people had some integrals even blank, which means they spend the whole time and couldn't actually figure out a mode of attack here. And I'm quite confident that had you seen how to attack these integrals, they weren't too complicated to actually compute once you knew what you had to do. Like if you saw, oh, it's just a substitution, you would have done it, and the numbers weren't crazy, they weren't anything weird. So I feel like if you didn't get an integral, it's because your approach was off. So let's actually talk about integration strategy. Faced with a random integral, here are the things that should go into your head. Pretty much in this order. I'll tell you when the order doesn't really matter. But see, a random integral shows up on a test, a quiz, or something like that. The first thing you're always going to think about is try to apply a basic rule. Always going to be the first thing that goes to your mind. What are the basic rules? What am I referring to? Things like the power rule. Things like, oh, the integral of 1 over x is ln of absolute value x. You know, the antiderivative of e to the kx dx is 1 over k e to the kx. Let's see. No, stuff like that. The rules that tell you how to integrate the basic elementary functions, right? That's the first thing you're going to want to think about. Of course, integrals are more complicated than that in general. So what I would say to do next, the second thing you're going to want to think about, if a base rule doesn't obviously happen, is to try to simplify it. So that a basic rule can be applied. So every now and then you might see something like, I don't know, just a silly random example here. Something like that, right? Doesn't look like a basic rule, however, it's one entity in the denominator which you can split up. So that would give you 1 over x plus x to the minus 4. And that allows you now to use a basic rule. That one would give you the ln. And this one would add 1 to the power, divide by the new power, and you can get the answer like that. Right? So it's not anything too complicated. But these are always the first two things you think about. The third thing you think about is substitution. It's always the third thing you think about. So try to substitute something to make the integrand simpler. Okay. Now simpler for us simply means looks like a basic rule, right? So you have something complicated, you do a substitution and suddenly it looks like 1 over u. Oh, now it looks like a basic rule. Now, back in Calc 1, the conventional wisdom was, make sure you can see the derivative somewhere else in the function. Now we're a little older, we can hear the hard truths. The derivative of your substitution might not be visible. This does not mean the substitution won't work necessarily. The substitution might not be the only thing that's going to get you to the answer, but it'll put you on your way. Typical example here, I don't know if this is typical, but the example that I came up with in my head just now. E to the radical of x. Now, it turns out the nicest way to do this is to do a substitution of u equals radical x. Your du is going to be 1 over 2 radical x dx. So you have 2 radical x du equals dx. And you'll notice that you actually don't have that there. However, by playing around with the actual substitution equation, you can modify the differential equation. And so this really just means 2u du equals dx, and then you can go back and plug that in. It ends up looking like u e to the u du, and that you do by parts or tabular integration, which is not difficult at that point. So substitution, the usual suspects fall into here, but remember, you don't necessarily have to have the derivative being present. Even the example over here, there was a point where I had to multiply by x over x to get the substitution to work. You should notice that things like these will pop up from time to time, but substitution as a general approach should be the third thing you think about every single time. Try to apply a basic rule. Oh, it doesn't work. Can I simplify it? No? What substitution would work here? That's always going to be your line of thought. Line of thoughts. Okay, now the following aren't in any particular order. But the first three, pretty much that's the order, every single time. That's what you think about in this order. So let's do an indented 4, integration by parts. And this is particularly useful, not the only situation, but you'll tend to want to think of this first rather than somewhere in the fourth position rather than something lower in situations where, like 1, you have a product of 2 different classes of functions. So like x sine x, right? That's a product of a polynomial and a trig function. That's 2 different kinds of functions being multiplied together. You see that, you would tend to think integration by parts is going to work, and usually it'll work. The second situation in which integration by parts might be the road you want to travel down is if you notice there is one function whose derivative is easier to compute. You know, almost all functions, that might be true. And the key word is it's also pretty convenient to have the derivative show up. A nice example to illustrate that guy was integral of arctangent, for example. That's not a product of functions, at least it's not unless you consider 1, the invisible 1, to be the other function. And you just realize, well, if I do integration by parts on that, where I'm taking the derivative of this guy, that'll give me a 1 over x squared. The integral of this is going to give me an x. The x over the 1 over x squared is going to be really nice for a substitution. And so it's easy to find the derivative, and it's also pretty convenient to get to the derivative. And in these two situations, integration by part is going to be pretty useful most of the time, right? Fifth thing you think about, trig sum. So if you see expressions, the three basic expressions, like x squared minus a squared plus a squared minus x squared, especially if these guys are trapped inside of radicals or something. Then you do the proper substitution for each one. So x equals a secant theta, x equals a tangent theta, x equals a sine theta or a cosine theta. You definitely want to avoid if odd power of x is somewhere else. Because then you should have picked that up in step 3. Regular substitution would work. So I'm talking about if you saw like x over the radical of 1 minus x squared, or x cubed over the radical of 4 minus x squared, things of that sort. You have an odd power of x to help you out. A regular substitution is going to do the trick. Probably don't think about trig substitution right away. Six, partial fractions. And this you'll see when you have proper, meaning the highest power on the top is smaller than the highest power on the bottom, rational functions, where the denominator factors. If not proper, reduce first. And this may eliminate the need to use partial fractions at all. That's pretty much the game you're playing in your head when you look at an integral, right? This is how you're going to determine its destiny. You always think basic rule first. If not, can I simplify to get a basic rule? If not, does a substitution work? Don't worry about too much of the derivatives, is very visible at the moment. Run through the substitution and see, can you finagle it to get it to work? With enough practice, you will know when you'll build up the intuition for when it would work rather than not. In by parts is what you should think if you have two different classes of functions multiplied together, or you have one function where its derivative is pretty nice to use. Avoid if you have an odd power of x separately. Partial fractions in the rational case. And we'll probably do this next week, but using that, what I'd like you to do is pick up a calc book, go to the review section on integrals, and just actually practice doing that. Practice mentally coming up with an approach. Maybe even go over your quiz, especially if you did wrong. Got a lot of these wrong. What you're going to do is, here you have 4 integrals. Give yourself 20 seconds. Can you get through the strategies for all 4 of them in 20 seconds? That's a good place to be, right? If you can figure out what you're going to try within 5 seconds of looking at an integral, you're fine, you're solid. It takes you more than that, probably need a little bit more work. We'll probably practice some of that next week. And I will see you guys then.
Thank you.